Hi, for today's lesson, we'll be learning about non-homogeneous second-order differential equations. A non-homogeneous second-order differential equation is a differential equation that has the second derivative as the highest derivative, and the equation is not equal to zero. The solution to this type of differential equation is the sum of the homogeneous version solution and the particular solution. So when evaluating a non-homogeneous second-order differential equation, we have y equal to yh plus yp. Yh is the homogeneous version, yp is the particular version. For our first example, we have d squared y over dd squared minus 5 dy over dt plus 4y is equal to e to the 4t. This can be written in the form y double prime. These two tick marks mean prime. This is the second derivative, so there's two tick marks. So y double prime minus 5y prime, first derivative is y prime, plus 4y is equal to e to the 4t. Now when evaluating this, we will solve this twice. So we will solve the homogeneous version, where this equation is equal to 0. And then to find yp, we outright solve the equation equal to this term. So for the homogeneous version, we have y double prime minus 5y prime plus 4y is equal to 0. In order to solve this type of equation, we need to let y equal to e to the rt. This implies that y prime is equal to r e to the rt, and y double prime is equal to r squared e to the rt. So now that we have this, we can substitute these values back in for the y's respectively. So r squared e to the rt minus 5r e to the rt plus 4 e to the rt is equal to 0. We find that they all have this multiple of e to the rt, and this can be pulled out. So this leaves us with the characteristic equation r squared minus 5r plus 4 is equal to 0. So when you get this form, it's just called the characteristic equation. So now that we have this, we find that we have two factors, r minus 1 and r minus 4. So r minus 1 times r minus 4 equals 0. This implies we have two r values, r is equal to 1 and r is equal to 4. However, y is equal to e to the rt. So this is not our final answer. So we have our first y is equal to e to the t, and our second y is equal to e to the 4t. The homogeneous version is the sum of these two. So yh is equal to c1 e to the t plus c2 e to the 4t. These constants are here, and they do change based upon initial conditions. To find the yp, the particular solution, we're going to go back to our original second order differential equation. So y double prime minus 5y prime plus 4y is equal to e to the 4t. Now we're going to let y is equal to k e to the 4t. So when thinking about this type of differential equation, we want this to eventually equal this. So this is going to have some form of e to the 4t in it. We're not sure yet, so we're letting k equal some constant. So let y is equal to k e to the 4t. Y prime then is equal to 4k e to the 4t. Y double prime is equal to 16k e to the 4t. These derivatives were found using the chain rule in calculus. So now using this, we can substitute these values back in, respectively. So 16k e to the 4t minus 5 times 4k e to the 4t plus 4k e to the 4t is equal to e to the 4t. And then after simplifying, we'll get 0k e to the 4t is equal to e to the 4t. And then we get 0 is equal to 1. This may look like a dead end or we did something wrong, but we realize now that our answer will not be a constant times e to the 4t. It will be something else times e to the 4t. So with this in mind, we can now let y is equal to kt e to the 4t. For many situations like this, t, like multiplying by t works, but we need to verify that it works for this particular differential equation. So now we let y is equal to kt e to the 4t, y prime is equal to 4kt e to the 4t plus k e to the 4t, and y double prime is equal to 16kt e to the 4t plus 8k e to the 4t. These derivatives are also found using the chain rule. So now that we have these derivatives, we can substitute them back in. So 16kt e to the 4t plus 8k e to the 4t minus 5 times 4kt e to the 4t plus k e to the 4t plus 4kt e to the 4t is equal to e to the 4t. After simplifying, we will get that 3k e to the 4t is equal to e to the 4t. The e to the 4t's cancel out, and we're left with 3k equals 1, so k is equal to 1/3. Now that we've gotten our k value, we realize that our particular solution is 1/3 t e to the 4t. Because down here we had y is equal to k t e to the 4t. So our particular solution is 1/3 t e to the 4t. Now that we have our homogeneous solution and a particular solution. We add these together to get our general solution. So our general solution to this differential equation is y of t is equal to c1 e to the t plus c2 e to the 4t plus 1/3 t e to the 4t. It is okay to write this just y, but this is a function of t, so it may be helpful to write it with t in these parentheses. For our second example, we have a d squared y over dt squared plus 4 dy over dt plus 13y is equal to negative 3e to the minus 2t. We have something very similar to this differential equation. So now we can rewrite this as y double prime plus 4y prime plus 13y is equal to negative 3e to the minus 2t. So our homogeneous version is y double prime plus 4y prime plus 13y is equal to 0. Like the previous example, we're going to let y is equal to e to the rt, y prime is equal to r e to the rt, and y double prime is equal to r squared e to the rt. So now we will, after working this out, we will get our characteristic equation, r squared plus 4 plus 13 is equal to 0. It isn't as clear as what the factors are, but we can use the quadratic formula. This is a very similar form to the quadratic formula, so we will use this. So r is equal to negative 4, where 4 is b, 1 is a, and c is 13. So r is equal to negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 13 over 2 times 1. This implies that r is equal to negative 4 plus or minus the square root of negative 36 over 2, which is equal to negative 4 plus or minus 6i. This negative in here, this makes it an imaginary number, and the square root of 36 is 6. So r is equal to negative 4 plus or minus 6i over 2, which is equal to negative 2 plus or minus 3i. Now that we have this r form, we go back to our y, and our y is equal to e to the rt. So our y is going to be equal to e to the r times t. This plus or minus, actually, we see from this that we will get 2y, so y1 and y2. So we get a y1 is equal to e to the minus 2 plus 3i t, and our y2 is equal to e minus 2 minus 3i times t. And then we see that our y1 is equal to e minus 2t times e to the 3ti, and our y2 is equal to e to the minus 2t times e to the minus 3ti. Now that we have imaginary numbers and exponentials, we can use Euler's formula to break this down into cosines and sines. So e to the I theta is equal to cosine theta plus I sine theta. And a quick note here, using Euler's formula, e to the 3ti is equal to cosine of 3t plus I sine of 3t. And e to the minus 3ti is equal to cosine of minus 3t minus I sine 3t. And the cosine of a negative angle is equal to the positive angle, so this is equal to cosine 3t minus I sine 3t. So the important thing to take away from this is that our homogeneous version will be some sum of a cosine and sine. Now please notice that these both have the same real part, e to the minus 2t, and our homogeneous version is the combination of these two. So we will have constants like the previous example. So our y homogeneous is equal to c1 e to the minus 2t cosine 3t plus c2 e to the minus 2t sine of 3t. Our theta was 3t because this is the number being multiplied directly in front of the imaginary part. And our real part is e to the minus 2t. This may be confusing at first, but with more practice, we'll become much better at it. Now that we've found the homogeneous version, we need to go back and solve the particular version, the original differential equation given. So y double prime plus 4y prime plus 13y is equal to negative 3e minus 2t. Now we're going to let y equal to k e to the minus 2t, so this must equal this, so this form right here must equal some constant times e to the minus 2t, or it is somehow related to e to the minus 2t. So we're going to let y equal to k e to the minus 2t. Y prime is equal to negative 2k e to the minus 2t, and y double prime is equal to 4k e to the minus 2t. After simplifying, we get e to the minus 2t times 4k minus 8k plus 13k is equal to negative 3e to the minus 2t. We get 9k is equal to negative 3. This implies that k is equal to negative 1/3. Unlike our previous example, our particular solution will be a constant times e to the minus 2t. So our particular solution is equal to negative 1/3 e to the minus 2t. And our general solution is the sum of the homogeneous version and the particular solution. So our general solution is y of t is equal to c1 e to the minus 2t cosine 3t plus c2 e to the minus 2t sine 3t minus 1/3 e to the minus 2t. So I hope this helped you in understanding how to solve non-homogeneous second order differential equations and in understanding what they are. Thank you very much for watching, and I hope this helped you in a differential equations course.